In the fourth part of this section of statistical geometry, we'll deal with outliers. So outliers are important. First of all, they could be just erroneous data, but they could also be anomalies, parts that are basically values that are not part of the population or background population that we're studying. In that sense, we also have to make a difference between outliers and extreme values. Extreme values are, let's say, a legitimate part of the population that are just very high. Well, outliers are anomalies, and so anomalies can be very important. For example, in mineral prospecting, we're really looking for anomalous data, something that stands out to the with regard to the background. So discovering those outliers, those anomalies, is important. There are a number of papers that we'll be using in this presentation. Outliers. Some of these are just applications. I think those are very interesting. Particularly want to point out also the application of outliers in terms of compositional data in this paper by Moser, and then the fundamental papers by Rousseeuw in terms of calculating or determining unmasking SSS multivariate outliers using robust statistics. So let's first look a little bit about talk a little bit more about visualization of multivariate data, because in such visualization we can also then possibly detect outliers, and then we can go ahead with more rigorous quantitative methods to determine what those outliers are with some statistical confidence. So this, here's a data set that's quite well known and famous in statistics and was created by Fisher. So Fisher is, of course, the father of say modern statistical methods, and so this data set was used to illustrate linear discriminant analysis by saying, okay, I have a number of irises. I have 3 groups here, and in those 3 groups I make 4 measurements. One has to do with what's called the petal, and the other the sepal. And in both cases, we take, say, the length and the width of those geometries. In total, we have 150 observations. So the first question is, how do we visualize all this information? Well, one of the common ways, of course, is to make this matrix where we color. In this matrix, we cross-plot the various, basically the various variables. So length, width of the 2 structures, sepal and petal, and then in there we can color those then with the particular group that's been studied, namely the type of flower that we're dealing with. And so let me put up my pointer. And what we notice then, of course, in this diagram is that we notice correlation between certain things like width and length, and we all notice grouping. And so that's an interesting observation. Looking at this information, of course, it's a little bit more cluttered. And so question is, are there simpler other plots to do that? And so one of those plots is called the parallel coordinate plot. So in the parallel coordinate plot, the first thing we have to do is to rank the variables that we're dealing with. And that ranking, of course, is going to influence this plot. Once we've done that ranking, then the second thing that has to happen is some kind of a scaling. So certain variables range, say, from 2 to 4, others range from 4 to 8, others range from 0 to 2. So we scale that such that we can all compare that. And then basically what we do is simply connect the lines of each belonging to each point. And so what we then notice is that we get a bit of sort of more a single plot that gives you some insight into the multivariate structure of this data set. And in doing so, we notice a few things. First of all, we notice the 3 groups seem to be appearing reasonably well. So that means to be linear combinations of these variables that are indicative of that group, and that's something that is relevant, and that's something that we can study, for example, with principal component analysis. Possibly also, and later in the course, we talk about logistic regression that allows us to predict the class from the various data that are available. And so the other thing we can, of course, notice is possibly our outliers. So this would be lines that look like completely independent of the lines that we are observing. So in summary, for the principal coordinate plots, we could say that all variables are rescaled, that it allows us to some degree linear dependency detection. That has mostly to do by the fact that we're plotting piecewise continuous lines. Definitely, we could look at subgroup detection, see, for example, in what group what variable is varying the most and which variant is the least, and outlier detection. And the outlier detection will come back later. Of course, this all depends on the ordering that you use. It becomes more limited when you have a large amount of variables. Then certainly the ordering becomes quite relevant, and so that may then require some tuning that itself may require further insight into the problem. Okay, let's look at a little bit more of a sophisticated example where we look at remotely sensed data and exploring basically the variability in remotely sensed data in terms of classifying those data into land uses. So here's just the example being taken. So as you know, remotely sensed data, we obtain various spectral bands that then allows us to determine the land use. And so the way it's done is that we record the remote sensing data, we establish the various bands, and then also we do some ground truthing. That means we go and we sort of verify, or even visually you could look at that there are certain land type covers that are available. And in black are the areas where we are not certain at all, let's say, and the other ones are just sample data, target data, or target variable. So here we notice that we have in total 6 classes: water, agriculture, etc. So the question now is can we use this to classify the rest of the image, or possibly a larger area? So here we see the parallel coordinate plot of our data. So here we plot the various bands, the spectral bands. So we have 7 bands here, and the class together. And so we immediately notice natural grouping into this parallel coordinate plot. We also notice a few other things. Is, for example, that the class bottomland seems to have a very narrow set of spectral bands or overlapping with that, so it's probably easier to classify that. While if you look at agriculture, we see much more of a spread, and also we see much more an overlap, so it may become more difficult to classify those two or separate those two. So of course, discrimination, now we can also see which of the variables is informing most of the classes. For example, if we would know that we are in band 5 and we're in this range, and it's pretty clear that we have urban. And so again, that can be used to understand possibly sensitivities in terms of predictions and variable selection in terms of making predictions. So if we would be doing a classification method, and so I'm not going to talk about the specific classification method. That's something we'll talk about in the next session on data aggregation. But imagine that somebody has developed a classifier, and so this classifier we then classify based on our spectral data, our image into land use. Now, it's clear from the previous PCP plot that we have some uncertainty regard to that classification. And so, therefore, it's useful to also create probabilities of being in a certain class. And so that's plotted over here. So here we have 2 different methods of classification. I believe this is this is a probabilistic method. This is a method here based on fuzzy sets and fuzzy membership, and I'm going to go into the details of that. But imagine you have 2 classifications. You get 2 maps. For example, you would then, if you have 6 classes, you would get 6 probability maps, each for each class. So here we look at the probability of agriculture. What's more common in all this, in image analysis in particular, information science, is to look at entropy. And so in the next slide, I will explain why that is. So the problem with probability in general is it's a variable. Probability it's a property that if you have probability equal to 0, then you're certain, and a probability of 1, you're also certain. So it would be nice to create a variable where 0 means certain and anything else means more uncertain. And so entropy is a function that would do that. So entropy is defined as minus the probability times log probability, and that for each class. So n here is the number of classes. So in this case, if you just have a coin flip, if the coin would be unbiased, then we would find that the entropy is 1. So imagine the coin would always fall on the tail side, then entropy would simply be 0. If it would always fall on the head side, entropy would be 0 as well. So that's why we like entropy better in terms of a degree of uncertainty, at least by visualization, than say probability. If you have more than 2 classes, then the maximum entropy is simply equal to the log of n. So after having done this analysis, we can now create some more PCP plots. So in this first PCP plot, we plot the Shannon entropy for agriculture 2 class. So this is that entropy, and we also plot the probability here of the various other classes. Because there's some variation in the entropy, what we'll be doing is classifying the entropy itself, is saying the entropy is between this amount and that amount. Then we classify it with a certain uncertainty level. So this would mean low uncertainty, and this would mean increasing uncertainty. And so in doing so, then we can look at the relationship of the uncertainty level of, say, the agriculture class with the probabilities of any of the other classes. We can then also do the same thing for the bands. So we can look at uncertainty on the bands. Uncertainty on the uncertainty level, again, for agriculture class in relationship to bands. And so to visualize that a little bit better, because we see some spread and overlap in here, one operation that we can do is brushing. It basically essentially selecting pixels in the image that, say, for example, have a low uncertainty level, but not all of them. And that would be done simply by through visual means. So just looking at the image and going in with a brush and essentially marking those areas we are interested in. And so then get a better insight into what determines this low uncertainty in that class, and what bands are associated with such low uncertainty, and what bands would be associated with high uncertainty. And for example, we see that high uncertainty could be due to a high variation into this particular class. So this class is not well discriminating essentially the agriculture. So again, this is another visualization means by which you can get a little bit more insight into the multivariate structure of data sets. Okay, let's now turn to the outliers and how outliers can be treated and visualized. So let's first look at visualization. Where could that show up? So here's a simulated data set of geochemical analysis. It's called the GMAS data set in the paper by Filzmoser. And in that case, we actually simulate the outliers so we can just know where they are. And so here are the map of the various data and the various simulated values. And we notice here on the right-hand plot where the outliers are, this plot here. Okay, so it's a simulated data. How's the simulation done? It's simply done by looking at basically, you could do it by log ratios. So we could create ILR. We can draw from, say, a bivariate normal distribution, and we just put some extra points here on the outside. So it's clearly that these points don't follow that normal distribution, and so they have to do with a very high value, say in this component, and that can also be visualized in the ILR system. So in ILR, in terms of X3, for example, X3 could be gold or silver, and that will be determining that anomaly. So here it's pretty obvious, but that's the point of the example, is to have an obvious example and see where visually it could show up. So graphically, it would show up in the parallel coordinates as well. So if you plot all these parallel coordinates, then we notice that there's trends in these parallel coordinates, and there's samples that are just not following that trend. So if we color the outliers in there, we notice very clearly that, in particularly the red ones, which are the severe outliers, that we have something that's completely not following the structure. And here we plotted in a gray black scale, it's even more visible. So in this particular case, we're looking at outliers that were, for example, determined by gold distribution. And that then would show up in the biplot. So if you make a biplot, so this is a biplot of all the data, and this would be a biplot of the outlier data. And so you notice in the gold case here, in the gold variable, we see that a lot of samples are associated with that. So that means an indication of anomaly associated with gold. Well, there's also some other associated with some other elements like arsenic. But this kind of data tools like PCP, outlier detection, are also used in different other areas of geosciences. Here is a nice paper in Computers and Geosciences about big data visual analytics, where we focus now not on data, say, collected in the field, but data generated by computer experiments and computer simulations. And so this is more and more common, of course, that we do Monte Carlo on computer simulations, and that creates a huge amount of information. That information needs to be displayed. And so in this particular case, we're now displaying the various outputs that we get from these runs, and also possibly related to various inputs. And that allows us to study sensitivity analysis more visually, possibly looking at relationships, say, between these various components. So for example, here we're looking at latent heat or log runoff, basically a computer model that simulates climate. Okay, let's now turn to the main theme here. We have now have ways of visualizing outliers in multivariate and compositional data. So now we'd like to come up with some quantitative methods of determining which sample is an outlier anomaly and which sample is not. A number of interesting papers, as I showed in the previous slide. The idea of outliers and the idea of using what are called robust statistics was pioneered by Rousseeuw, and there are several very important papers that were published there on detecting outliers in multivariate data sets that are very important and being used in a lot of applications. So the way we're going to proceed here with these outliers is that we have an outlier is basically defined as a value that's not part of, say, the main population. So then we have to define the main population first. And we'll be working here with the multivariate normal distribution as the sort of the background population, or possibly a mixture of multivariate normal distributions. You could say, well, you know, that's an assumption, and that's correct. So that we have to work within an assumption of multivariate normal distribution. There are, however, methods that allow us to deal with extensions to that, where the data is not multivariate normal, and particularly when you have very skewed data. Then, of course, we possibly have to do a transformation of variables of the individual variance, or scaling of those variables into a more normal range, and then dealing with the outliers. That's also what we saw with the PCP plot, is that we have to do some form of rescaling. Of course, what we can rescale is transform is the bivariate nature of the distribution. So we can only do transformations on univariate, rank preserving transformation on univariate distributions. And so the very fundamental, of course, concept that quantifies this relationship between variables is a covariance between any two variables, or if you have multiple variables, say p-dimensional problem, as is shown here, then we have to define the variance-covariance matrix. And so this is its definition. And then, of course, in reality, we'll have to calculate that using the data that's available, and we get the empirical version of that. So a couple of properties that we will recall is that it measures only linear dependency. So if your multivariate data set has dependencies that are not linear, then we cannot apply this concept. That obviously the covariance is scale dependent because it has the variance in it, and that there are, as a consequence of the first two, basically that there are nonlinear dependencies that may show up as zero covariance. So even if we say that we have established that covariance is a good way of describing dependency is linear, we still have the issue of estimation. And estimation of covariance is highly affected by either outliers or extremes, and that's a problem. And that has to do with the square nature of things. We use variance as a measure of variation, which is a square difference. When you square big numbers, you get huge numbers. When we want to detect outliers for extremes, then we have an issue because essentially the extremes are affecting the covariance calculations, but are a legitimate part of the population, and the outliers affect as in the same sense. So it becomes difficult to discriminate. So we have to do something about this estimation of that covariance structure. Correlation, just a quick recap here as well, is that correlation is simply a standardization of covariance. And so here we get then the correlation matrix, which is calculated directly from the variance covariance matrix. So if I assume our background population is multivariate normal, then the only thing we have to know would be the covariance and the mean. And so this is then this nature of that distribution. So then, of course, you could say, okay, so in order to estimate that population, we have to estimate the mean and covariance. The problem there, of course, as I mentioned in the previous slides, is that the estimation of this covariance matrix is maybe problematic. And certainly in the presence of outliers, it becomes difficult to determine the background population. So we would like to remove those outliers from the analysis in order to establish our background population. That requires identifying them. An interesting property of this multivariate normal distribution is if you do the following transformation. That means you take the square root of sigma and multiply that with this amount here, then we get a new variable, and that new variable is now suddenly unstandardized. It's uncorrelated. So this has a correlation matrix that's basically this guy here, which is the identity matrix. So what does this mahalanobis transformation mean? This is going to be important into our analysis because it allows us to transform a problem of dependency into a problem with independency. One thing we noticed in the previous slide is that in the first part of the equation of the multivariate normal distribution, there was a determinant, namely the determinant of a covariance matrix. So what is this determinant, or what does that try to establish? So the determinant of the covariance matrix can be seen as a generalized variance, because the thing is that we have to have some kind of scaling in the front of this distribution that accounts for variance. And so one way of doing that is to calculate a single scalar that is essentially as a representation of variance. To understand this a little bit better, let's look at the bottom example here. So imagine you take a determinant of this unitary matrix. So we have that, then the determinant, of course, is 1. Well, if we now have another correlation matrix where we have higher correlation in the sample set, then the determinant is less. So, and that makes sense, right? Is that in terms of variance, this has much more variation because of the lack of correlation than this here. So in the 2D example, then we can establish that the determinant is simply a product of variance, but then corrected for covariance. So this is a measure of variance of the correlation matrix, and that's something we'll be using later when we're determining what an outlier is. Another interesting thing that we need to look at in terms of the multivariate normal distribution, if that would be samples of a multivariate normal distribution, then we can calculate contours of equidensity lines of this, in this case, bivariate normal distribution. And so here we can understand a little bit better what this mahalanobis transformation is trying to do. For example, you can imagine that if I take the center and I'd look at something that's equidistant from the center, then this point here lies on the same contour as that point. So we could say, it would be logical to say that this point is equidistant from the center than that point, at least in terms of measured by the density of the distribution. And so what a mahalanobis distribution does is it takes this ellipse and transforms it into a circle. And so on that circle, then we have essentially, we can measure these distances directly. So the mahalanobis transformation is a way of doing that. So here we just have an example where we summarize some of the statements we've made before, is how essentially a covariance is affected by calculation of outliers or extremes. So here is just another data set, soil data set, and so it's clear that, for example, that if I would use all the data values that are available, then the correlation coefficient would be 0.66. While if I say I assume these are outliers and remove them from the analysis, let me put my pointer. If we take these values and remove them from the analysis, then suddenly my population changes, and essentially the correlation coefficient drops substantially. So the question is essentially, should we remove those from analysis? If we assume the background population is a normal bivariate normal distribution, which would we call outliers and what we call samples of the population? And so that's the question. So we'll be applying that to the Kola dataset. It's a dataset I introduced in the first lecture in the introduction. Again, it's a soil data set with a number of XRF and other types of measurements that provides a chemical analysis and elemental analysis of this data set. So we have here, I think, 50 or 100, I don't quite remember. We have a large data set, multivariate data set. So the first thing we have to worry about in analysis is not to confuse univariate outliers with multivariate outliers. So in the univariate outliers, you could say, well, let's say I take the lowest 2% and the highest 2%. So I take some quantile and then I cut off the distribution at that amount, and then I get basically outliers. And if I do that, of course, for both univariate distributions, then barium and calcium here, then I get the square, and everything else outside the square is now an outlier. If you think multivariate, however, in higher dimensions, then you can say, well, let's look at the 98th percentile or equidensity function, and let's say I'd like to have 2% outside of this ellipse. Then suddenly I get points that are different. For example, these points here, which were deemed outliers because they're not within the square, suddenly are no longer outliers. Or vice versa, these things that I thought that were not outliers are all of a sudden are outliers. So when we deal with outliers, we can't, in a multivariate structure, unless we have independence of the various variables, we should be mindful in not using simple univariate tools. So how will we start dealing with this in a more quantitative sense? So what we'll be calculating is a distance, and this is the mahalanobis distance. It's the distance that I introduced earlier. That means the distance adjusted for the elliptical nature of the normal distributions. And so to transform that, to calculate that distance, we have to, of course, account for the covariance information that's there. And so this is if this is the mean, the center, then calculating the mahalanobis distance is done as such. So if I have n data points, then I have a matrix now, which is a distance matrix with mahalanobis distances in that matrix. So one thing that is interesting to notice is that theoretically these distances are essentially follow a certain distribution. If the underlying background population is normal distributed, then these distances follow a chi-square distribution. And so it then makes sense, of course, to calculate the quantiles of this chi-square distribution with the empirical quantiles calculated from your data. And so then you transform essentially a multivariate problem into a univariate problem, and that calculation can be done. So where we, of course, likely are going to see the deviation is in the tail of the distribution. And so that's what we're looking for. There's a bunch of methods to look at that. I'm not going to talk too much about the math here and what is done. I'm going to just look at some examples that illustrate some of these concepts. So the problem, of course, with mahalanobis distances is the same problem as with calculating the covariance. That is, it's affected by this inverse covariance, which may be unstable when you have extreme values. And of course, or outliers, and of course, we're trying to detect outliers. So we're in this catch-22 situation. So the way we are going to circumvent that problem is essentially by looking at calculating the covariance matrix with lesser data and trying to eliminate information or outliers from our population or data set until some point where we cannot longer eliminate them. And so the question is, what is that point? How many data N essentially will we be removing? And so to determine that, what we'll be calculating is the determinant of the covariance matrix as we are removing data from our analysis. Because the determinant essentially is a variance of the covariance. And so we'd like this variance of the covariance to stabilize. And what we expect is that as we start removing outliers, is that this variance starts to stabilize. And that's what we were hoping for. So the idea of Rousseeuw is to essentially calculate robust mahalanobis distance instead of the mahalanobis distance. So the standard mahalanobis distance would just calculate the covariance matrix based on all the information. So the point of view here, or the way to proceed with this, is to say, let's calculate the mahalanobis distance now, not just all the data, but less amount of information, and then calculate and then call that, let's calculate the covariance matrix based on less amount of information. And then the distance calculated from that, let's call that a robust distance. So here, we use the data set that's in the Rousseeuw paper. Is essentially a manufacturing data set with, I think, 9 variables. And so we get a 9-dimensional space in which we have a 9 by 9 covariance matrix that we then calculate. And then based on our covariance matrix, we calculate mahalanobis distance for each of the samples. So we see that we have about 700 samples in this particular case. So we notice indeed there are some large distances in there. And the question is, okay, where do I draw the line? What do I call extreme, what I don't call extreme? And so from this, there's not a clear grouping that we could say is maybe I need to go a little lower and say remove this of the analysis. So the way it works is to look at the determinant of the covariance. As I said, the determinant of covariance is a measure of variance. And so what's expected is that as I remove more and more information or data from my analysis, then I would expect that this covariance determinant, this variance becomes stable. Becomes constant. The problem, however, in higher dimension is that we can't just say these are the n highest data points because that's only possible in a univariate space. In a univariate space, you could indeed rank information. In higher dimensions, you can't rank information anymore or rank samples. And so we run into a combinatorial problem, is that there are many combinations of samples that should be essentially studied. In essence, we should be studying all the combinations, and that's too much. So typically what they do is study a few. And even if you study a few of those, and this is well established here, then you notice that the step boundary is not necessarily the amount of samples, but it's related to it. Then we see a convergence in that covariance. And so from that, we can then determine the number n, where that convergence occur, and draw that line. Once we've drawn that line, we can calculate the robust distances by recalculated covariance matrix. And so here we see now plotting the mahalanobis versus robust distance. The first thing you notice is that the robust distance is much larger than the mahalanobis distance. That's good in terms of determining outlier. And that if you look at robust distance, now we have 2 populations. And so this is clearly now the outlier population. So these could be then removed from our sample. Okay, so once we have robust distances, then we can look at the chi-square distribution. We expect that these robust distances would follow a chi-square distribution, and any deviation from that would be then be outliers. And so there's another way of removing the same outliers is to look at that. Here we see the ordered robust distances for the quantile of the chi-square distribution. And so if I take a few of these points, then I remove them from analysis, then I get something that's much more, a quantile that's much more of a straight line. And so then I can plot these points. Here we notice points into a specific bivariate plot. Notice the points are over here. This is the background population. We can start now looking at where exactly these are located, and that could be an interesting area to go look, whether it's for mineral prospecting or pollution or some other application. Okay, to sum up, we've discussed outliers as anomalies, and in many of our analyses, they're just not errors. They're actually can be quite interesting, can be as interesting as extremes. They're different, though, is in the sense that you're not part of a sort of background population, where extremes are just very high values of the background population. We looked at a couple of visual aids, such as principal component plots, to detect outliers, or possibly also relationships and multivariate structures that are interesting. We developed a method, or we introduced a method for robust statistical collation and identification of these outliers, and the way it was done by the mahalanobis distance and by robust calculations of these mahalanobis distance as a statistic, and then possibly comparing it to the chi-square distribution.